This is Project 4 by Joshua Webb, Patrick Nemina, and Owen Champion. Alright, for our project, the constraints are we're going to have two 1-meter bars, and one is going to be made out of aluminum, and the other is going to be made out of iron, and they're going to be in a series. And they're going to be held at a constant 20 degrees Celsius. Then both bars are going to be heated up, each a temperature of 120 degrees. Alright, so next we have our theory, and these on this page are just constants, so it's quite simple. The thermal expansion for iron is 12 times 10 to the negative 6, and the thermal expansion for aluminum is 23 times 10 to the negative 6. The Young's modulus for iron is 200 GPa, and the Young's modulus for aluminum is 70 GPa. So these are just known constants. Okay, so for our equations, this one is for the equation of iron, and we see that the change in length for iron is 12 times 10 to the negative 6 times 1 times 100, which gives us 1.2 millimeters. Now, to find the stress, there's a formula, and the formula is described here, but I'm going to write it down so you see what it looks like. It's in order to find the stress, we do change in temperature multiplied by the coefficients of thermal expansion, which is basically just coefficient of aluminum subtracted by coefficient of iron, Fe. It's a really bad E, but divided by it's divided by 1 over the Young's modulus. So for iron and aluminum, so 1 over the Young's modulus of aluminum plus 1 over the Young's modulus of iron. So, see right here, find the stress. We do the change in temperature multiplied by the coefficients of thermal expansion, which is R2 on the numerator, and it's divided by the Young's modulus of iron and aluminum, which is what's on our denominator, 1 over E of aluminum and iron. Alright, now moving on to our second equation, which is the equations for aluminum. The change in length is 23 times 10 to the negative 6 times 1 times 100, which gives us 2.3 millimeters. The stress of aluminum is found the exact same way we found the stress of iron, which is to find the stress you need to change the temperature multiplied by the coefficient of thermal expansion divided by 1 over Young's modulus, which we did in the last slide. I won't do it again just to save time, but yes, so that's how you find the equations for both our aluminum, the equations of stress for both our aluminum and iron, I should say.
The calculations were completed. We found that the change in length of the aluminum bar would be 2.3 millimeters. This would bring the final length of the aluminum bar to 1.0023 meters. Due to the force from the iron bar expanding as well as the aluminum bar expanding, the aluminum bar feels a compressive stress of 181.4 megapascal. Likewise, after doing the calculations for iron, it was found that the iron bar would stretch by 1.2 millimeters. This would have the final length of the bar become 1.0012 meters. Just like the aluminum bar, the iron also feels a compressive force of 181.4 megapascals from the stretching of the aluminum bar and the stretching of the iron bar. The aluminum bar stretches further than the iron bar. This is expected since the thermal expansion of aluminum is almost 2 times as great as iron. Discussed in the constraint section, it is given that the bars are held together by 2 walls and they are placed in series. This means that the bars are placed end on end. This means as the 1 meter bars expand, they are forced to push into each other, creating a force between them. The forces that the bars feel are reaction forces. This means that whatever force one bar feels, the other bar will feel an equal and opposite reaction to this force. This gives us the number of 181.4 megapascals of compressive force that is exerted on the bars.
Does the data support the diffusion flux equation? So now we're going to analyze the data in the table and explain how it supports the diffusion flux equation, which is diffusion flux J equals negative diffusion coefficient D times the concentration gradient dC over dx. The diffusion flux equation describes how particles move from high to low concentration. So this means if you have more particles on the one side of a barrier, they'll naturally spread to the other side. This is shown in our data because at the beginning, we start with 0 on the right side, and after we open the barrier, the particles start increasing on the right side. The concentration gradient is the change in concentration over the distance. So the steeper the gradient, the faster the diffusion. Our data supports this gradient rule because the diffusion happened faster in case 1 than in case 2, which was more concentrated with particles, 200 to 50. Going back to the data in the previous slide, it depicts the starting particles on the left side starting at 200 or 50 in some cases, and then it spreads out to the other side at rapid speed in picoseconds. Does the data support the diffusion coefficient's temperature dependence? So now I'm going to explain what happened when the temperature decreased and see if it supports the temperature dependence of the diffusion, which is expressed by the equation diffusion coefficient D equals max diffusion D naught times exponential of negative ED, which is the activation energy, over Boltzmann's constant kV times temperature T. The temperature dependence equation shows how faster movement occurs at higher temperatures due to increased atomic energy. And the exponential term in the equation makes even small increases in temperature cause large increases in the diffusion rate. The data supports this, and it shows that in cases 1 and 3, they have the same gradient, and their concentration both start with the same number of particles on the left side. The difference between these cases is that the first one is at 300 degrees Kelvin, and the third one is at 50 degrees Kelvin. The differences in temperature cause significant changes in diffusion, so this means that the data collected supports the diffusion coefficient's temperature dependence because it proves that the temperature significantly affects the diffusion.